Hello students, welcome back to our geography class. I do want to say that if my voice sounds a bit low or if I pause a lot, I might forget some words and take a second to remember some of those words. Or if you're wondering why the room is a bit darker, it's because I have a bit of a pre-migraine going on. That's just kind of what happens to me pretty often. I have chronic migraines. Sucks, but what are you gonna do? The reason I wanted to film this anyways, because I do have some free time today, and of course free time can be a bit hard to come across, so I wanted to make sure to film this lesson. On that note, if you guys do have any conditions or any accessibility issues that I can help with in terms of presenting, please let me know. And I hopefully can get some help with some closed captioning, or if anyone wants to help with translating the lessons into another language, please make a note of that in the comments section below, or you can contact me on Discord by, there is a link in the pinned comment section. That being said, this is lesson 4, Forces of Change. If you guys are following along in your textbook, this is probably going to show up in chapter 2 of your textbook. At least it does for mine. I really like the forces of change. For me, this is the most interesting part of geography. It's basically going to be how things like formations are made on the planet and how they interact with each other. And then also, can they interact with us? If so, how? Can we exacerbate it? If so, how? For me and my, educational background, it's in stuff like buildings, environmental science, geology. So for me, this is the most interesting stuff, just how we can be safe and thrive in terms of our city or other neighborhood in relation to what's going on with the Earth. That being said, we're going to go ahead and start with plate tectonics. Plates in this case are going to be just big chunks of land, and tectonics is a word from Latin, which originally comes from Greek, and it has to do with building or constructing things. So really, this is chunks of land that make stuff. That's what plate tectonics is. As you guys probably know, our Earth does not stay the same. So you may know of a supercontinent from the past called Pangaea. It's probably the most famous supercontinent, but there's other ones like Gondwana, and there's many others as well. So this is something the Earth just kind of does. It comes together, it goes apart, comes together, pulls apart. Just cycles of what the Earth does. There's different ways that the Earth can change, and the first one we're talking about is plate tectonics, which is an internally driven change, or inside. What's driving it inside? It's going to be that hot liquid rock, which we know as magma. Just in case you're not sure the difference, magma is when that liquid rock is underground. Lava is when that liquid rock comes out from underground. So basically, we've got hard land floating on liquid magma. Kind of fun, right? And I know we don't think about it all the time, but sometimes I do remember it, and I just think, kind of like surfing. It's interesting, right? Kind of fun. So I did make this a bit bigger. I should resize it. Sorry about that, guys. But basically, as these plates are moving and interacting with each other, we have different things that are created, such as mountains, for example. And so that's this image that we can see here, and then I do want to make it a bit larger so you guys can see it a bit better. So there are 3 basic type of plate boundaries. This is where 2 plates connect, they meet together. One of them is called a divergent boundary, where it goes away from each other. You can think about it like divorce, for example. Divorce, divergent. So it goes away from each other. That's how you can remember that term. When we see this on the planet, this is basically a spot where the magma is coming out from the Earth. And because it's so far under the ocean, that water's very cold, that liquid rock will harden quite quickly. And so this is kind of where this land gets produced. And so as it comes out, it starts moving. Remember, the plate is moving away from the other plate. And so we end up creating new land. The opposite of this is going to be convergent, like to congregate, to come together. Now, one of the plates will actually go under the other plate just because of density. and the plate that goes under or goes below is going to be the subducting plate. So it goes below here. We end up with something called a trench, the most famous of which is going to be the Marianas Trench. And so you can think about this as where the land goes back into the mantle. It's going to heat up again, and then it's going to be recycled out of that divergent boundary. The transform boundary is also found in some faults. So every boundary is a fault, but not every fault is a boundary. Essentially, if you got two plates that meet together, that's going to be a boundary. And we still call it a fault, but it's also the plate boundary. But if we've got some plates kind of moving and squishing around, you'll get these cracks kind of in between. Those are faults that are not plate boundaries. A lot of those faults can be the transform type of faults. These are the faults that slide by each other. Sometimes they're called slip strike faults. So those are our faults. So all of this to kind of explain it, how this works together, predictions that we can make from it. This is called the theory of plate tectonics. Now I do want to review this. Hopefully it's a review, and if not, well, now you guys will know. A scientific theory is not the same meaning as theory in everyday English. When we say theory in everyday English, we're usually talking about something like an educated guess. So this is something along the lines of, if I'm a detective and I come across a crime scene, I can look at some of the clues, take in the crime scene all together, and use my past experience, my education, and anything I might have known about the victim or any suspects that maybe I had met them before, I have a record on them, anything along those lines. And I can say, all right, maybe the most likely cause for this crime is this thing. And I can say, I have a theory that the most likely cause for the crime is this thing. So this is really saying I have an educated guess, and that's going to be my starting point as a detective. A scientific theory is the end point. So once we have an idea or an observation that we make about some natural thing, we want to figure out what's causing that natural thing. So that's when we come up with a hypothesis, and then we start doing the experiments. If the experiments can help prove the hypothesis, cool. If it doesn't prove the hypothesis, we go back and refine it, more experimentation, and so on. Other people do the experiments, we write down the data, we compare the data, other people review the experiment itself. Was there anything we didn't control for? Does the experiment make sense? Are there any variables we didn't consider? And if it seems to be pretty good, we can say, all right, so this hypothesis appears to be the case, and we've now proven it, essentially, although proof is really a word for math, but just colloquially we'll say we have proven it. But if this is true, then we should be able to make predictions about future cases or things that we can find in nature that should be a result of this process. And then we do find those things. Our predictions end up coming true. And so once all of that happens, for the way for us to explain all the data, the observation, the experimentation results, the prediction results, that's a theory. So for example, there is a theory of gravity and there is a law of gravity. Typically, just for our purposes, if we're talking about laws, usually we're talking about some kind of mathematical equation. The theory is the explanation for all of that stuff we talked about. So this means basically plate tectonics is not a guess. It's not, well, this is what we think is happening. It's, we have lots and lots of evidence to show that this is happening. Just so we know. So this idea actually came about earlier in the 20th century, but really it was proven in the 1960s. It's not that long ago. I know you guys might be thinking it's, you know, a while ago, but it wasn't that long ago. So this is one piece of evidence that we have here, was finding different fossils in different areas. Now, back when I was a student and they said, oh yeah, we know plate tectonics is true because, you know, look, South America looks like it fits into Africa. And I thought, that's not very convincing. What if they just look that way? Whatever. That's not what they're talking about for fitting together. Yes, they do have sort of a puzzle piece connection, and that's sort of helping with it. But really the connection we're talking about is that we have similar fossils of animals and plants that are found across different continents, and we know that these are not capable of traveling across large expanses of salt water, for example. We also have different types of rock formations. And so we have very similar, or the same actually, rock layers and formations in parts of like Eastern South America and Western Africa. Also in places like the eastern side of North America and parts of the western side of Africa, but also parts of like Northern Europe, Western Europe, those kinds of places. So fossils that are across these areas, the same exact rock formations, and also this thing called there's a basically magnetic signatures that get into these rocks, and we used to think that the magnetic pole actually moved. And that wasn't really the case once we figured out, because again, once we have that idea, okay, these different magnetic signatures are because of the pole moving. So magnetic north is moving, and that's what's causing that difference. We should be able to make predictions, and those predictions did not come true. It only started to make sense once we said, what if it's not the pole that's moving? What if it's the land masses that are moving? So if the land masses are moving, we should be able to make predictions, and then those predictions ended up being correct. So that's one way that shows you its progression to a theory. So plate tectonics can make different stuff like new continents, like we talked about. So this is kind of fun here, if you guys can watch that while I take a sip of my drink. So we can see here, Australia is kind of coming up. Australia used to be a lot more south. Pretty interesting stuff. It can make new mountains. This is the Indian subcontinent crashing into the Asian continent, and this is creating the Himalaya mountain range here. Kind of cool. We can create new seas or lakes or rift valleys, and that's with those divergent type of plates. So again, we've got those three types. Now, sometimes the plates can get stuck. Typically, they just kind of move slowly, but sometimes they can kind of get stuck. And then when they release that energy, when they finally have enough energy behind it to get themselves unstuck, we end up with an earthquake. So I did want to show you a couple of these videos, and I do have to kind of move this here. All right. The videos do not have any sound. Now just imagine being in this pool, okay? So not a great time. People are kind of freaking out. It's a bit of a big one here, but I mean, just imagine being in that water. It's a good thing there's nobody in there. So this is, I mean, this is pretty scary. Imagine you're on this ledge, basically, right? It's barely wide enough for two cars to pass by each other, and then suddenly we get this kind of earthquake. Parts of the road that we're on can collapse, so that white van on the side could fall, right? We also got those rocks falling from above, so this is just a really unfortunate situation. Now we have some people that are trapped in a pool. I believe this was in Nepal. And so that's going to be along that kind of Himalaya mountain range. We do get a lot of earthquakes along the plate boundaries, and I will show you guys a map of that. If you guys are outside and there's an earthquake, just stop, go to the ground. Otherwise, you can get thrown to the ground. And that, I mean, that's a stupid way to break a bone, isn't it? Because you decided to stand up during an earthquake. Not a great time. If you are driving, of course, pull over. I would not get out of my car. These guys got out of their car while they were driving. I would not do that. One of the reasons I wouldn't do that is because these power lines here, if they fall down and they hit me, any number of things could happen. Physically, just getting hit with the pole, that's really damaging to my body, of course. Or I can get smacked with that electricity. That's not a good time, right? So if I'm in my vehicle and I'm not touching any of the metal, then that's going to be a lot safer. By the way, a lot of people die in earthquakes, in major earthquakes, because of fires. So that movement of just the earth tends to crack or pull apart any gas lines. And then when we have things like the power lines collapsing, that creates a spark. And so this is how we end up with a lot of fires. So there's a lot of fire deaths, which is something to definitely be aware of. Here we just have another video. Again, you want to get to the ground, but I feel like this is such a tragedy when we have these really old buildings and then they were not able to withstand the types of earthquakes. This one, the security camera or CCTV, this one's shaking around. We're gonna stop there. That's too much jostling. If you guys have any issues with flashing lights, like I do, that's just a bit much. We're going to go ahead and return back to our PowerPoint, and I am going to readjust this. Cool. If you do want to see the full video, there will be a link to that in the details section below. Now you can actually see some of the fault lines. Other ones you want to check on like Google Maps. Then you can see the satellite view, and you can actually see them, and we'll check them out in future sections. But it's a pretty fun thing. So because these are basically breaks where the earth is, this ends up creating a point for magma to come out. And so because of that, almost all of volcanoes are actually on plate boundaries. And so we can see this here just to give you guys an idea and make this larger. So I want you to look at this side here and also this side here. This is going to be the ring of fire because it's almost entirely a ring of these plates. We can also see here around between South America and the African continent. So we have another boundary as well. And so if we actually look at this here, we can see between Africa and here's South America on this side. We do have a few underwater volcanoes, but here is what we were talking about, this ring of fire for the Pacific Ocean. I mean, so many volcanoes. Another notable area of volcanic activity is going to be here in Iceland. And as I mentioned, this is pretty much where we also get most of our large earthquakes around every year around the world. So pretty interesting to be able to just look at this and say it's, you know, almost exactly the same as our plate boundary map. Interesting, but not surprising, right? Other types of change that we're going to get are weathering and erosion. These are going to be external, so they're not inside the earth, but they're going to be on the surface of the earth. So weathering is the breakdown of rock. This can be done with wind, ice, rain, water, salts, etc. If you haven't, what's it called, trypophobia with all the circles, please do not look at your screen. I will tell you when it's okay. But otherwise, this is what salt weathering looks like. This will happen close to where we get a lot of salt in the air. So anytime you're near an ocean or a salty sea, you're going to end up with this type of salt weathering. Pretty specific. This is the only thing that's going to cause this type of many different circles type of weathering. If you guys looked away so you didn't see all those circles, you can look back at the screen now. This is ice weathering. So the way that ice weathering works is you have a small crack or a medium crack or any size crack really in a piece of rock. Water will get in there, and then of course, as we know, when water freezes, it expands. And so that expansion happens and cracks the rock further. And so over time, as more water can get into those cracks and then it freezes and it pushes apart, we end up with it just splitting the rock entirely, some cases. So we can see that here. And what we end up with is really, really sharp splits. So this is going to make a really sharp separation. And if there's no other weathering, no other, for example, salt weathering, for example, or wind erosion that's going to happen, then you can kind of just put it back together almost. That's kind of how that works. This can also happen in places that get a lot of snow or rain, and so this will damage the asphalt. This will damage the concrete in addition to damaging rock. Erosion is going to be when the broken down rock is moved. So basically, weathering can happen by itself. Erosion can kind of sometimes happen by itself, but typically weathering and erosion happen together at the same time. So as something is being broken down, it also is moving it. So for one example, rivers. For some reason, this is not animated. This was animated when I made it. I don't know why it's not moving right now. But rivers will erode rock. And we end up with a really smooth erosion for this because water kind of wears things away very smoothly, very gradually. So as this river is breaking the rock down, it's also moving it at the same time. So this weathering and erosion happen together. Oh, now it's working. Well, great. Now we can see it. Kind of fun. Fabulous. Here's another way to look at this, and this is probably going to be closer to a sea or to an ocean. So this is another way to get that kind of moving water to create erosion. So it is being weathered and eroded again at the same time. Rain is going to erode rock, and I included this because there is this idea that the Sphinx is actually 36,000 years old as opposed to only a few thousand years old. And this idea that the Egyptian civilization started way earlier, something ancient aliens. So that's not the case. What happened here is we do have some water erosion, either from rain or from water that kind of leaks over, such as from the Nile River's periodic flooding every year, kind of leaks over. And what we get is this erosion on the Sphinx enclosure. We don't get it on the rest of the Sphinx. And so the rest of the Sphinx over time has had some updates and some changes to it. But really we're getting that only on this inside rock, or sorry, the rock enclosure. So this is not caused by lots and lots and lots and lots of rain, but more like this trickling over. But I still wanted to use this because I wanted to talk about that idea. And I also wanted to just show you because it is a really good example of that type of dripping water. So we can see here it's sort of uneven. It's got lines in there. It almost actually looks like rain itself, doesn't it? Like a rock interpretation of what rain would look like. So there is a lot of movement in there. There's little cracks in there, and that's kind of how that fits. So this is what that rain erosion, that trickly water. That's, I guess, what I would rather call it is trickly water. Because the erosion is going to look very similar whether it's rain or whether it's like floodwater spilling over. So we're going to end up with that sort of undulating kind of look to it. Wind is going to erode rock, and we're going to end up with this mushroom shape. So you don't have to write it down, but pause and try to guess, why does it create this shape? So if you've thought about it, the reason we end up with this is because the wind is carrying particles. The particles that are heavier cannot be carried as high. So the heaviest, biggest particles are going to be towards the ground, and that's going to do more of like, imagine like a bigger fist punching that rock. So this is going to eat away at the bottom of the rock, where the smaller, finer particles that are up in the air, higher up in the air, those are not going to do as much damage. It's sort of like the Hulk fist versus like a baby's fist. Obviously, if they're all punching at the same time, the Hulk is going to do a lot more damage below as opposed to this baby fist towards the top. And so we end up with this mushroom shape. That's how they're going to look. It can look kind of smooth, but it can also have a jagged or uneven kind of look. It's not very sharp. We're not looking at it like that sharp ice erosion. So this is still pretty smooth, but it's really uneven. So you can see there's like these dips and kind of, you know, almost like a depression and a mountain ridge almost in there, if you can think of it that way. But again, the big deal is that mushroom shape. That's how you know this was done with wind erosion. If we're looking at just erosion, not weathering, this would be an example of sand being eroded by the wind. So it's just being moved. It's not being like broken down necessarily. We also have glaciers that can erode rock. And so if we end up looking at this mountain example here, so we've got some mountains that hang out, having a good time, and then a glacier shows up. A glacier is just a big block of ice. The big difference between a glacier and an iceberg: iceberg is in the water, glacier is on land. And so this is going to literally press down, and it's also going to create some of that ice weathering as well, depending on how long it took to form. Once all of that goes away and melts, we end up with these interesting kind of circles. Okay, so there's some parts that are really flat, there's parts that are kind of curved. We're not going to get a lot of that undulation that we saw. We're not going to get a lot of these jagged, kind of uneven pieces. Another way that glaciers are going to cause this type of erosion and weathering is just if the glacier is hanging out on top of the land, and as it slowly moves, it just kind of flattens everything. It's almost like a big iron. So if you happen to live in an area that is really, really flat, there's no mountains, almost no hills, that place almost certainly used to be under a glacier. Those places also tend to be pretty good for farming, which we'll talk about in a future chapter. But that's because there's a lot of good stuff in the glacier. Once it melts, it puts it into the soil, and then it ends up being flat and nutritious soil, perfect for farming, right? So that's what we end up with. So just like the internal forces that we talked about, these external forces can also result in natural disasters. So if we're having erosion of dirt, that can cause landslides. So again, we're going to watch a video, and I do have to adjust this a little bit. That should be good. So we're just driving. It's only a minute long. Check it out. I mean, pretty good quality for 2013. It's a good dash cam. So it is raining, and we do have this hill here, this mountain. So now we've got this land that got dislodged, and ooh, there it goes. Ugh. Imagine being the person in that car. I would have peed my pants. I mean, let's be honest. So that's all that happens. Thankfully, these people are okay. But this is going to be one of the big dangers of rain. So if you live in an area like this, where you have a mountain or the side of a really big hill, and it's got a lot of dirt, not a lot of trees, and in some places we actually put nets over this to prevent this kind of spillage to happen, this kind of landslide, mudslide. If you don't have that, please be very careful as you're driving. If you can avoid driving when it's raining, avoid driving when it's raining. Another type of erosion that can happen is a sinkhole. And actually, we can contribute to that as well. So if we had put water pipes, for example, in a very sandy area or an area with just lots of dirt, not as many rocks, and one of those water pipes starts leaking or it busts open, we can end up eroding away the ground under the surface. And so then it creates this pocket of air, basically, and the top will just kind of collapse in. So we're going to go ahead and check that out here. Now, what I want you guys to realize is this is 46 seconds. And it just opens up suddenly. Good thing they had put those cones around it, right? Now, I don't know how long this area had been cracked, so I don't know how long those cones Those safety cones have been there. But once it starts to fall, it tends to fall pretty quickly. There are other similar videos, and again, they're around the same length of time. They're between 40 and 70 seconds long, where cars are just there and then maybe a car disappears. So you really don't have much time. Um, not not great. What I think is interesting too, just for fun, is you can see just how bendy the asphalt is. We tend to think about it as a really solid thing like concrete, but it's actually quite flexible, which is pretty interesting. That being said, that is going to be our last bit of information on the forces of change. If you guys have any questions that were not addressed here, please feel free to post that in the comments section below. If you guys have witnessed any of these or have lived through something like this, please feel free to share. And, you know, what were your thoughts as it was happening? I mentioned previously in another lesson that I was living in an area that got hit with a really big, like a now famously large earthquake. And at the time, it just wasn't what I would have thought, oh yeah, this is going to be, you know, one of the top earthquakes that people can kind of remember, or they end up in like those top 10 or top 15 kind of videos. Um but again, it's because I wasn't like right in the middle of it. Um, so for me, it just seemed like a really big earthquake just as a kid. And then we all went home from school. That was really what I remember the most from it. It just didn't seem like it was that big of a deal. But suddenly my mother was calling a lot of people. We were getting calls if we were okay. She was calling other family members and friends that lived in the area if they were okay. And that's kind of when I thought, this maybe is a little different than the other earthquakes that we have encountered. Um, but other than that, you know, at the time I didn't think about it. So, you know, when we watch these videos, we always think of like, oh, this is so devastating and so terrible. But we do have to remember there are people that are not right in the middle of it. So it can be really bad, but it also can be not as bad. And I think it's good to get all of those um different perspectives. And again, for us, really, this was the worst part of it was wondering if our family members were okay. This was before cell phones, really. They had cell phones, but they were super expensive, couldn't text or anything on them back in the day. So, you know, for us, it was a little bit worrisome. That was our biggest fear. So it wasn't, oh, is our house going to be there, but is, you know, our cousins going to be there? So that was our biggest concern. Anyway, guys, feel free to, again, just post what you like in the comments section, but make sure it is minor safe language. And again, you can join us in the Discord, join me on Patreon, and all of that good stuff. But otherwise, I will see you guys in a future class. Bye bye.